So, hi guys, it's nice to see that you are here, so many people. Today we're going to talk about 3 microservice patterns that you can use to tear down your monolithics. And there are some challenges with microservices. Of course, microservices are good, but how do you manage your nodes? How do you coordinate your nodes? And how do you ensure that you have your consistency throughout your nodes? And how can you test them? And how can you recreate erroneous states? I mean, we are programmers, so we never do anything fault, do we? Or not? At least, yeah, exactly. That's good. The blame game is important. So we're going to talk about 3 patterns here. We're going to talk about event sourcing. We're going to talk about something called materialized views and CQRS, which stands for Command Query Responsibility Segregation. I'm going to just briefly mention what it is now. So event sourcing is that rather than writing the result of something, for example, if you increase someone's salary with $100, you don't say salary is equal salary plus 100, but you say the salary increased by 100. That is a difference. You can replay that event later on, and you can see and trace the entire state that followed up to a certain salary for that person. Materialized view consumes these events and produces something that you can view. That is the current salary, for example. And command query responsibility is that you basically write and read from different objects. So the writing and reading is decoupled, and that's very important. So Emil here is going to show a demo of a booking system. By the way, I'm Per. I invented a bunch of stuff. I've been working with Java since 1.0. Live here in Palo Alto in California, and I have a blog. Make sure to check that out with millions of reads.
Yes, and my name is Emil Forslund. I also work at the same company as Per here, Speedment, and I'm also a developer living here in Palo Alto. My blog is called Age of Java. But I would also like to introduce our mascot, Spire. That's an open source mascot that lives on GitHub and has 3 years of mascot experience, and you can check him out later. So yeah.
Cool. Yeah. So what is Speedment? Speedment is something that can produce SQL queries from streams. Whoops, this is falling. Okay.
Don't lean on it.
No, I shouldn't. So if you have a stream, any stream, it can produce SQL. So you don't have to write your own SQL queries. You can just use streams. And streams are nice, as we all know by now, since Java 8, and even with Java 9, they're even nicer. So that is basically Speedment. And when you look at it, there is a remarkable resemblance between SQL and the stream operations. So you can really construct basically anything from a stream to SQL, and you don't have to live in this world of both languages. So I wrote an article about this in a recent issue of Java magazine. So if you want to know more about this, you can go online and check that out. You recognize the table, for example, there. Today, we're not going to talk about this so much because we're going to talk more about microservices. So I just want to mention what it is. It converts a stream to SQL. It does lazy streams. So if you create a stream that only consumes maybe 3 or 4 elements, you don't have to pull in all those result sets from the database. It only pulls in elements as they are being consumed. We have complete type safety, because when you construct your stream, you can't use an int if it's a string and vice versa, for example. And one cool thing is that you can use with parallel database queries. That is something really, really difficult to do with JDBC. And it's pure Java, and it supports both Java 9 and Java 8. So go to GitHub and try it out. And with that, I will hand over to Emil for pretty much the entire presentation today.
So yeah, thank you. I'm going to want to do most of the microservice stuff. So first off, I would like to explain a few terms that I'm going to use throughout the presentation, just to make sure that the general language and vocabulary isn't confusing anyone. So whenever we speak about a client, you might think that we mean an end user. But when you're talking about microservices, a client is everything that can invoke a service. So another service could be a client. So you don't make any distinction towards another service calling your API or an end user calling your API. They are all clients. You also have services, and services are things that can be called by a client. They are some kind of business logic that exists on its own, can either be deployed by its own or deployed on the same machine as something else, but it's still its own service. A service can exist in multiple instances, which means that you can scale it up and scale it down independently. So when we speak about an instance, we mean an instance of a service. And services can be accessed through an endpoint. And the endpoint is the kind of the URL that you see. It's the way you interact with the service. So that's just some short terminology. So during the course of this presentation, we're going to be talking about, sorry, I'm a bit too tall for this, I think. We're going to talk about something called a booking system. So this is our application that we're going to build here tonight. So the booking system's purpose is to allow users to book resources. And we don't really define what a resource is, because I want you to be able to imagine it into any kind of situation that you normally work with. But it could be car rentals, it could be renting the laundry machine at your living housing compartment. It could be any kind of thing that you want to make sure that users can book. We also are going to support multiple users. So there are multiple users out there, and there are multiple resources that can be booked. And we can only ever allow one user per resource per time slot, which means that our system must make sure that we can never double book anything. Users can also reschedule things. They can say that, oh wait, I mentioned I wanted to book this on Monday, I actually want to book it on Tuesday instead. Or they can completely cancel bookings at any time. So this means that the system must be resilient to change, that the user can change the conditions throughout its lifetime. And we are also constraining it so that every user can only have a maximum number of bookings open at the same time. So these conditions pose some challenges when working with microservices, since it requires us to keep the synchronous state between different machines, which is not really how you tend to do things. So the most easy way to implement this system would be to create a monolith out of it. And basically one single Java application that stores things in a relational database. Whenever the user sends a request, like a post, get, put request, and so on, we basically just authorize the request, see which user is doing this, then change the database depending on what the user did. And this is stateful, which is not RESTful, even if we're using post and get and so on to expose it. So this is the kind of thing we're trying to get away from. Monoliths that are difficult to maintain, they're difficult to test, they are hard to trace what is actually happening, because once the database state has changed, you can never really go back unless you start trailing audit logs or something like that. So it's difficult to kind of get a sense of what did happen on August 23rd when that bug occurred. That is kind of lost into the logs. And whenever you want to do any kind of maintenance, like you're regularly updating this product, you have to take it down or temporarily replace it by another service. And this can be quite difficult to maintain in a continuous integration environment. So this is the thing that we want to get away from. So if you were to visualize this kind of system, it looks quite easy. I mean, it's only 3 things that are interacting with each other in a very nice and clear way. So this should be great, right? Well, it turns out that once you start managing these kind of systems, it's not as easy as it seems, because first off, if you want to scale it up, you have to basically scale up the entire thing. You can't scale up one individual functionality in it. So that means more licensing costs, it means more machines for doing things that are maybe not really necessary. You also, it's not very responsive for the end user, because every time the user does something, every time the user wants to do something, they have to send in a request, and it has to go all the way down to the database and all the way up, sometimes multiple times, to respond to that single query, to authorize the user, to make sure that you're allowed to do that, and all those things. So a lot of systems I've seen take several seconds to complete a single business transaction, simply because you have to go several turns down to the database and back. And then people complain over the database, but it's not actually the database that's being slow here. It's the general design of the system.
Or the users.
Yeah, or the users. So this is the kind of, just to imagine the system we have today, so that we have potential to create improvements. We also have no graceful degradation of failures. So if I were to, unplug this one machine, the entire system goes down, and the user gets, strange error codes in their browser. So we want something where a single failure doesn't affect the integrity of the entire system. Basically, you can plug any kind of system out of the wall and the system will continue to work. So instead, we combine these three design patterns that we're talking about here tonight. And that's event sourcing, materialized views, and CQRS, command query segregation responsibility. Command query responsibility segregation, yeah, other way around. So instead of storing states, we're basically storing changes. So when the user wants to book something, we let them book it. We don't control if it's accepted or not. We take every event that comes in and we register it in the database. So the database is simply a log of events that have happened. Then when an event is consumed by one of the services, that service has to evaluate, was this event accepted or not? So this is a bit of a weird mindset, I know. You don't want to store things in a database if it's not supposed to be there, right? Well, it turns out that this solves actually a lot of problems. Because if you have one single log of everything that has happened, and you let every single service for themselves subscribe to this log of events and evaluate them every time they read them, it means that you can scale the services up to as many instances as you want, because all of them will have an eventual consistency. They will eventually be at exactly the same states. So to allow the user to interact with the system, you have to allow the user to get access to this event stream, allow them to subscribe to events as well. But the user doesn't necessarily have to evaluate events. They just need to know when an event has happened that affects them. And then they can request that from one of the view services to get a more recent view of the situation. The materials view is basically just, it's taking the stream of events and evaluating events, and if accepted, integrate them with the current states. So they have a state, they take a new event, check is this event correct, corresponding to this state, and if so, I integrate it, otherwise I throw it away. And in that way, you only handle one event at a time, you will have an eventual consistency. And the CQRS part, the last part, you have to keep the writers and the readers separate. The writer can never know the current state, and the material view can never affect the current state. You have to keep these two concerns separate, otherwise you will get dependencies that are going to be very difficult to unravel. So with the booking system, if multiple users go in and try to book the same resource at the same time, what is supposed to happen and what will happen in this system is that one of them will succeed, the other ones will fail. However, there will be a period of time before they all know who got it and who did not. So that's where the event log comes in. The user needs to be able to subscribe to the event log to kind of see that, oh, my event is actually being processed right now, but here is a nice message that shows you that we have taken the event and we're considering it. And if two bookings are changed at the same time into the same time slot, so both want to book the same resource at the same time, but the bookings already existed, they were just modified. One of the bookings should be modified and the other one should remain the way it was before. So they can be concurrently modified across the system. So at first, when you just visualize an event source system like this booking system, it looks a lot more complicated than it did when we had the monolith. So you can see that I have mapped out the client. In this case, it's the end user. And I've mapped out an edge service. We have a service discovery service. We have some kind of streaming service. We have what we call a calendar and a booking service, which is the read and the write services. We have the DB, and then we have a config service that stores configuration settings all over the place. There's like 7 services there. How can this be simpler than what we had before? Well, you have to take into consideration that every one of these services are really tiny in code because they only have one single purpose. So it's a bit to get your head around what they are all doing. But when you actually look at the source code for them, you find that most of these services are trivial to implement. You can basically just copy-paste them from the web and they will work in your case. You just might have to change a few parameters. Because when you get each service down to this particular one purpose, it's really easy to test and they're really easy to implement. So if we just visualize what is happening here, say that the user wants to, say they want to deploy this system first. All the services need to register themselves at the service discovery service. And in this case, I'm using Eureka, but you can use any kind of service here.
Well, what does it mean by register? Can you tell me more about that?
Yeah. So when a service registers itself, it tells the service discovery service where it is located and what kind of service it can serve. So it tells it, hey, I am at this IP address, I have this port, these are the REST endpoints that I can fulfill. The service discovery service doesn't really do much with this information. It basically just sends that information to the edge service. Says that, hey, a new service has been discovered, and it has these endpoints. And then the edge service kind of keeps a ledger of these, where can I route people that comes in? What services do I have? How many instances of those services exist? And then whenever a user requests something, the edge service knows where to send that request. So the nice thing with this design is that services never has to know where the other services are located or if they are even up and running, because they all have to just communicate with the service discovery service, and then the edge service is the one that is responsible for routing the traffic. So the client here wants to book a resource. So it contacts the edge service, which is the only service that are publicly available for the user. The edge service then routes that request to the booking service, since it's about writing something. It's about booking a resource for a particular time. The booking service then, at the same time, it sends, it kind of pushes the information down to the database, creating the event in the database as a new row. And it also, at the same time, sends back a receipt to the user that says that I have received this event, you have been assigned this particular sequence number. And that's really important because the client needs to be able to know when that event is being processed, what is happening. So the booking service does no evaluation. It doesn't say that this event was allowed or not. It basically just registers and returns back a receipt. The DB then the information goes from the DB down in the calendar, either by a push or by a pull. It doesn't really matter for the design of the software. And says that, oh, there is a new booking event here. Then it's up to the calendar. If it decides to accept or deny the event, in either case, it sends it down the stream. And in this case, the stream is a WebSocket, so the client can subscribe to it. And basically that this is the event I received. I have decided to accept it, or I have decided to reject it. And that then goes down to the client. If the event was accepted, the client can then look at the event and see that, oh, my request was accepted. So I want to see the most recent view of the system. So I send a request that I want to see the latest calendar view. It's like the last week of events, where my event should be located. It goes down to the calendar view, and the calendar is returned with the modified states. So this is the basic setup of the system. What you get for advantages from this is that services can be scaled independently. If you notice that it's getting a response from the calendar service, that's the one thing that takes time from the system. You don't have to scale up the booking system. You don't have to scale up the configuration server or the database. You can basically just scale up the calendar service. So if you notice that some part of the system is taking more time than something else, you can scale up that individual service.
So you mean that you can just add another node and that will go to the service discovery and will be a part of
yes.
the yeah.
So if the calendar goes slow, you just deploy a new instance of the calendar service. It will be discovered by the service discovery. The edge service will get a notification of this. It will start routing traffic there as well as the old one. And then you have basically doubled the amount of capacity you have. So yeah, that's really nice. The user also gets immediate feedback. I mean, the user doesn't have to wait until the event goes all the way down to the database and back, being evaluated and all that. The user can get a response immediately from the first the booking service that says that your event has been accepted and it's being processed. So that allows the front-end developers, for example, to show a nice animation, for example, if while waiting, and it allows them to get a really responsive feeling of the system. Services can also be maintained separately. So if you're working on the system and you're implementing it, if you're working on the booking system, you don't even have to have the source code for the calendar system running. If you want to deploy a new instance, you're not affecting the already running instances. and you can kind of hot swap them, add a new instance, remove an old one, and the system will remain intact. Also, if something goes wrong, if one service fails, for example, there was a bug in the booking system, so suddenly an erroneous input came in and all the booking services went down. Okay, well, the user will still be able to see the calendar since they can still access the calendar service. So this is a really important thing for the resiliency of the entire system, that one error should not affect the others. So of course, there are some services that are in this design more important than others. So if the service discovery goes down, for an example, soon all the services will not be able to recognize each other. But the edge server might still function for a while the services have the same IP address as they had before. So the system can remain intact even without the service discovery for a while, unless you start killing processes all over the place. So if we are going to design this as a booking service, instead of having a relational database with multiple tables for every kind of entity in the database, we try and put everything in the same table. And this is really important because we have to be able to replay it in one defined order. So we only have one table called booking event, and it contains all the information about that event that happened. The one service that can exist in multiple instances, but the one service that writes to the database does no evaluation. It might be able to sanitize some HTTP request or something like that, but it never does anything that requires it to know about the state of the system. So everything that's a valid just HTTP request is basically inputted into the database. The database then numbers the events so that they can be read sequentially. So the database gives every new event a number so that we know that all the clients, independently of where in the world they are located, they will all consume the events in the same order. Another service evaluates all the incoming events when they have been numbered by the database, and they materialize them into a view that the user can query. And the system is eventually consistent across all the instances. So to describe a little bit more about the first pattern here, event sourcing. So we have mentioned that the relational database doesn't store any states. It never stores that this user has this username or anything like that. It only stores the information that is changed since the last state. It also doesn't store if the state was accepted or not. It only stores that this is the thing that the booking service saw happening. So you don't need any update or delete statements. You only need insert and select, because you're never going to change anything since that was the truth at that time.
Okay, so you're saying that the database is basically a queue?
Yes, so the database is handled as one big persistent queue. You also don't have any indexes except potentially the primary key, which is the sequence number. Because indexes in this case only tends to slow things down. If the database has to update the index every time it does an insert, it's going to slow down the writes. And the reads are not going to go through the database anyway. They're going to go through the materialized view. So your entire database design is collapsed down to one table with no indexes and no joins. It's quite a simple design, actually. And you don't have any trouble with conflict resolution, since the only thing the database has to do is basically just increment an integer and an insert. So the database can handle thousands of writes per second, even if you're using an open source database like MySQL. And since events are evaluated when they're read, the reading of the events does not affect the reading can be scaled up independently, and the writer does not have to know anything about the current state. So you never have to synchronize with the writer. The writer can just sit there and know nothing about the system. It can just write everything into the database. So to the second pattern, the materialized views. The end user never queries the relational database. They only query the view. So one request to the materialized views does not cause a request to the database. And that's an important thing to get into your head, because that means that the scalability is extreme in this. You can have tens or hundreds of millions of users pinging the system, and the database can stay just fine, because the database does not get any requests per request from the user. It only gets requests at the timed interval when the read services, the materialized views, are querying results. When a new service is started, a new materialized view service, it loads all the events that have happened from the beginning of time from the database. And this process can take a while. In some cases, with our service, it can take up to a minute to load all the events. But that's okay, because there are usually other services that are available and can take in traffic. I'm not sure I understood the question, but you were wondering if there was any coupling between the writer and the reader? Mm? Yeah. Mm. If you want to change the schema structure, you do have a coupling in the sense of the design of the system. And I'm going to explain how to solve that later on.
It's not a materialized view in a database. It's a materialized view in the memory. Some people might think that there is a concept for certain databases that it's called a materialized view, but this is another concept.
Yeah.
Yeah. Yeah, then you start to have a lot of coupling. So we don't want that. We want really simple services that can really do a very small thing. And if you introduce a monolithic like coherent caching, I think then we're pretty much back to square one.
But that's definitely something that we can discuss afterwards. So in this case, once every second, events are being pulled from the database and merged into the view. And now some people might be thinking, well, polling is a bad thing. We have had bad experiences with polling a database, especially at a timed interval. So I just want to take a moment to kind of put up the math here. When you don't have any indexes on a database and you don't have any joins, you're basically just having one table with an incrementing integer. How many requests per second do you think that database can handle? Say that you're running a single instance of MySQL, for an example. Just throw out a number here. The one there's
5,000 per second, maybe?
Yeah, not reasonable to think. 5,000 per second, it should definitely be able to handle.
On a laptop?
Yeah, on a laptop. So if you have 5,000 requests per second as a capacity, it means that you can have 5,000 materialized views polling this database if they are, polling at at different time intervals. So if you can have 5,000 materialized views, and every materialized view is just an in-memory view of the current state, and every materialized view should be able to handle quite a lot of traffic, you can kind of get a sense of the total amount of users you can have in this system. And this is just with one single node of MySQL. So polling the database is usually a bad thing, but not if it's polled from an internal service that can exist in a few thousand examples. So when events are evaluated, if they're accepted, they are merged into the view. So it means that the materialized view service has to have all the rules regarding what to expect from an event. It has to be able to evaluate that. And that's kind of the one thing that's a bit tricky to get right with this kind of design. Because the rule set tends to change, and you have to kind of be careful when you change it to make sure that you're not affecting previous events. So also, views are eventually consistent across all the instances. Yes, when an event is consumed and it's supposed to be materialized in the view, then you apply all the business rules for this event. So say that the event says that user 1 tried to request the laundry machine at this date, and another event said that user 2 tried to request the laundry machine at that date. What the materialized view does, it takes the first event and sees, is the laundry machine available at that time? Yes, it is. Okay, I accept that event. And then when the second event comes in, it looks at the laundry machine and looks, oh, it seems to be booked at that time, so I reject that event. So that's what I mean with accepting and rejecting. And that's done when materializing. It's not done when you're entering into the database. I would register it in the materialized view. I would not register it in the database, because that would create a coupling from the materialized view to the database. And it's only the booking service that's allowed to write to the database. So yeah. So the third pattern, CQRS, it comes into this particular query here. So it stands for Command Query Responsibility Segregation. A command is something that's writing, something that's changing the state. And a query is something that's interested in the state. And the general idea of this entire design philosophy is to never allow those two to be on the same service. So the writers, they are never allowed to know about the current state, because that requires them to query something, and that destroys the pattern. The reads are never allowed to write anything. Like you say, they're never allowed to register anything in a database, because that creates another dependency. So both services can exist in as many instances as they need, and they never need to synchronize with each other, because all the materialized views are eventually consistent, and the writers are not allowed to look at the current states, which means that the information can go in one single direction all of the time. Yeah, we just use the relational database as a persistent queue, nothing more. So some of you might be wondering, why do we use a relational database at all? Why not NoSQL? So it basically comes down to about the same thing. When you take away all the things that are slowing down relational databases, like joins, foreign keys, and indexes and such things, when you're simply writing to it, the performance is usually about the same as writing to a NoSQL database. So it comes down to a matter of taste, actually. What is easiest for your team to manage and to deploy? And since the performance of the relational database is very rarely a bottleneck in the system, even if you were to see some performance gains by replacing the database, that's usually not what the best way of improving this performance of the system. So to the implementation of this booking app, I know that you've been waiting anticipatedly for this, and I'm going to go a bit, fast-paced over it. But I want to first say that all of the source code I'm showing here today is available on our GitHub page. So if you want to look at it afterwards, you can just go there, and there is a repository called Event Sourcing Demo, where you can see all of these. But first off, we used MySQL to store the event log, and Spring Boot to create the REST API. We use Eureka for the service discovery, and Netflix Zool for the Edge service. We also use Project Lombok to reduce the boilerplate in the system, and Speedment, our own product, to write and query the database using Java 8 streams. It looks like everybody put up their phones, so I'm going to stay on this slide for a little while.
By the way, the repository that Emil mentioned is under GitHub/Speedment.
Yeah. So yeah. So short, how it works. If you want to scale anything up, you just launch those processes as new. Spring has been configured to generate a random port for each service, so you can basically just launch as many services as you want, potentially in AWS or in Google Cloud or something like that. When a new instance comes online, first it starts by downloading the event log from the database. So we'll start pulling in data, about 1,000 events at a time.
Now I have a stupid question again.
Yeah.
So what if we have like millions of event logs or trillions?
Yes. So that's when we use something called snapshotting. Snapshotting is not covered yet in this example. I just didn't have time for it. But if you want to develop a snapshot service, it's really easy to introduce in this model. It basically just have the REST API that itself just subscribes to the events from the event log. Every now and then, like once every hour, once every day, it just saves the materialized view down to a file. And then when somebody requests the most recent file, you just serve it to them.
So you mean you can restart from that position?
Yeah, so you can restart. Since the order is always the same of the events, it's quite a trivial task to start from one particular time in the sequence. But I might get to implementing that service as well. So when the new service starts, it downloads all the events up to the current time from the database. And sometimes this might take up to a minute or so. The service discovery then picks up that there is a new instance of the service available. So I'll send a notification to the Edge service to start routing traffic there. And the Edge service will continue routing traffic there until it starts getting weird exceptions that the service is no longer available. And in that case, it basically removes it from the route. So it's an easy way to scale up the system, easy to scale down. You just start processes or kill processes. And the system will remain in what capacity it can during those circumstances. So for the SQL table that we're using as the event log, there are a number of things here that are interesting to note. First off, we use something called a sequence number. That's basically the number that the database gives every incoming event so that they can always be replayed in the same order. And this is also the primary key in this case. We also have a column called version. That is something I learned the hard way, that if you don't introduce a column called version, it might be really difficult to change the database schema later on. And I think that was what one of you were kind of hinting at. If you want to change the database schema afterwards, it can add some trouble implementation-wise. So what I recommend in those cases that we've been doing is that you basically update all of the materialized views at first, one at a time, to support both the old schema and the new schema, and separate the events by using this value of the version. Then when all of them has been updated, you can deploy them one at a time, since they can both handle both worlds. Then you change the persistence logic, and then you change the database schema to support this new version, making sure never to lose any information, because you can never remove anything from the event log. So you can, for example, add a column that has a default value, for example. That's allowed if you increment the API version. And then when you've done that, you update the writers, so that the writers can write by this new standard. And in that way, you have a coordinated way of updating the system. But as you can imagine, making changes to the database schema adds a lot of pain, so try and never use it unless you have to. So one way of making sure that you don't have to do it unnecessarily is to not store anything that might change in the future in the event log. Also a truth learned by experience. So in this case, you might notice that it's not really storing any vital information. It's just storing binary 16, which is UUIDs in MySQL. So you're basically storing that there is a booking somewhere with a particular ID, there is a user somewhere with a particular ID, and there is a resource somewhere with a particular ID. I don't know what the name of the resource is. I don't know what the username of the user is or anything like that. I only know that this is an user that I can identify. If you start adding other information to the log, you might get problem later on. And we also store the book from and book to, basically because we need that to evaluate events that are coming in, if they are allowed or not. So for implementing the relational mapping, we use Speedment, which makes it really easy. You just run a single Maven goal and will generate all of the classes that you need. And it's Maven Speedment tool. I had 2 talks earlier on this other one about that, so I'm not going to go into any details here. But the short version is that Speedment generates booking implementation, booking managers, and so on. And it's similar to how JPA does things, except that with Speedment, we generate the boilerplate for you, with JPA generates the database from the code, so it's the other way around. And Speedment is designed to work with the Stream API, which works really well in this case. So when Speedment starts, you connect to the database in a graphical dialog. You just press generate, and you have 95% of your application done already. So that's basically the things we said. Oh, and the last thing, we also have an open source plugin for integrating with Spring. So if you use that plugin, we'll also generate all the Spring configuration needed to set up the database. And
everything that's been used today is open source on GitHub. Yeah.
So the booking service, nothing new here. 2 things to note. We enable service discovery, and we make it a Spring Boot application. That's just to set up the application. Then when we want to implement a controller for actually inserting things in the database, we just auto-wire in the manager that Speedment has generated. And then we use a Spring configuration value that's called API version that defaults to 1, just so that we can easily change it in the future if we want to programmatically add a new API version. When we want to, we also use Lombok here to kind of set up a boilerplate for the booking request and the booking receipt. The 2 things that are sent out from the booking service. So when a request comes in, we want to return a booking receipt, and we want the request to be formatted as JSON. So we use Jackson together with Lombok here. So this will generate all the getters and setters for us. We also add a few helper methods. It's called new booking event. This creates a new event, sets the user resource and such from the request coming in. I use the Java 8 time API here. You might not be familiar with it, but basically the user specifies, if we look at the previous one, times as an offset date time, which means that they can specify which time code they are referring to when they say that I want to book that at 8 o'clock. And then the server localizes that time to its own time zone before inserting into the database. And then, of course, you need to make sure that the server is running on the same time zone as the database. Creating a booking is with the REST API is very simple. We wrap a Speedment request to persist the row into the database in a create receipt to get a response to send back to the clients. This is all the logic required to persist things in a database. You might also notice that we set the type to create booking. We never do anything other than persisting, which means that if the user wants to update a booking, we don't update any existing rows. We basically persist a new row and set the type to update booking. And then we use the same booking ID as the previous one. When you want to delete a booking or cancel it, what you do is basically send a delete request with the UID of the booking that you want to handle, and then we notify that as a cancel booking request. So if we want to test the service right now, we just do a curl command to that URL, and we say that, hey, I want to post to the booking system. I have this user, this resource, this booking from, and this booking to, and I want it to be persisted. And if you want to add security, like you probably should to this, I would suggest you use JSON Web Tokens to handle it, because that's a really RESTful way of handling user authority. And it has built-in support in Spring Security. So in this case, when I send this request, I get a response back that is nicely formatted with the location tag set to where the booking is going to be located once it's accepted or rejected, as well as the sequence number and the event ID given to it. So this allows the client to hook up to that URL and start to show a nicely formatted message to the user. The calendar service works similarly. We just enable the Eureka and we enable Spring Boot. We then set up a booking view, which is going to be our materialized view. I use scheduling, so enable scheduling and service to make it a Spring service. And then you can see here that the materialized view comes down to just a basic hash map, which maps from the UID to the booking. I also have a few listeners to be able to send them further on to WebSockets without hawking the update loop. So then again, use Lombok to create the booking and the booking confirmation that is going to be stored in the view, just to avoid all the boilerplate of setters and getters. So the booking confirmation is what is sent back to the client over the WebSocket to be able to notify the user that the booking has been accepted or denied. And it's just an enum in there with accepted or denied, as well as all the information about it. I also added a string message at the bottom, just to allow the server to add information to the user, like the request was denied because somebody else had booked this resource. Also to make it easier to develop a front end that's showing relevant information. And then I added the post construct to be able to load from the database when the service starts, before it's going online. And I'm scheduling a poll every second. The actual loop that is polling, you saw the poll for events method, it's using the Speedment stream, so just streams over the manager handling the events, filtering out every that has a sequence number greater than the last event, limits that to 1,000 elements, and iterates over them. Oh yeah. Yes. It it materializes the data into memory. So if you have a lot of events regarding the same booking, they are going to be collapsed down when materialized. But yeah, it loads in memory. That's the hash map before.
So why do you have the limit 1,000 there, Emil?
Yes, it is basically because I don't want to hang on the database too long. So we noticed after a while that when you start a new service for the first time, it might take a while to load all of the events that have been processed so far, unless you use snapshotting. So this was an easy way to allow other logic to come into the loop and not hang too long. So it just takes 1,000 at a time, and then uses an atomic boolean to kind of switch back and continue working in case there was more events. So just a small hack to get that repeated loop. And you can also see down in the right here the SQL query that Speedment generates. So it's actually a nicely formatted query, even if you use the predicate and the limits. So the calendar service is quite easy. We just auto-wire in the booking view, the one we created earlier, and then we expose 2 different REST endpoints for requesting all the bookings or requesting bookings by particular URI. And we also have so you can book by find all the bookings for a particular resource or all bookings for a specific user. And was just something we added to make it a little bit more interactive. So when we test this, we do it by using curl again. Just say that, hey, I want to read this booking. And we can see that the booking has been accepted by seeing the status of 200. And then we can see the information, which user was it that booked this, what was the resource, and so on. It looks like I've spoken too much, but I was always done with the presentation. Please feel free to look up Speedment afterwards, the library we were using to do the database logic here. And like I said, all of the examples here today are fully working on GitHub. So yeah, thank you.